Hello everyone, today we are going to talk about comparison tests. There are more tests, right? We have lots of different tests for series because as I said, there are not too many formulas to calculate the sum of series. So we need to know if the series is convergent or not and then use estimations to kind of find the sum, right? So we are going to start with comparison tests and there are two of them. One is called the direct comparison test. What is a direct comparison test? I'm going to give you example first, and then I'm going to set up actually like how the test sounds. Well, you probably remember that a series 1 over 2 to the power of n starts with 1 to infinity, which is like 1 over 2 plus 1 over 2 square plus so on, which is also known as G series, geometric series, is convergent. Why? Because r is equal to 1 over 2, right? You are raising 1 over 2 to the power of n, actually, every time, every term. So this series is convergent. Now the question, what this series? Is it going to be convergent to 1 over 2 to the power of n plus 1? If you just modify it a little bit, add 1 over here. We kind of understand that actually, if you compare terms of this series and terms of this series, you're going to see that these terms are going to be less. I'm going to do comparison. There. We know that 2 to the power of n plus 1 is greater than 2 to the power of n. Just obvious, you add 1, you're going to make it greater. So if you divide 1 over 2 to the power of n plus 1, it's going to be less than 1 to the power of. Well, why does it happen? Because if two numbers, like for example, 2 is less than 3, then 1 over 2 is going to be greater than 1 over 3, remember? Yeah, so this less. What does it mean for us? It means that every partial sum of this series is going to be greater than every partial sum of this series. I don't know, let's maybe label this as series A and this as series B, right? Sum of series A and sum of series B. So it's going to look like the whole series BI is going to be less than the whole series AI, just because every term is less and then everything is less. But we do know that this, the top series or this like the bigger one is convergent and we even do have the formula. Remember the formula was looking like this, 1 over 1 minus R, right? Well, it's actually A over here, but in our case, our A is equal to 1, so we are going to have 1. So in our case, we are going to have 1 over 1 minus 1 over 2, which is going to be 2. Yeah. 1/2, and that converges to like 2. That's a little bit strange. Supposed to be converge to 1. I'm thinking that I kind of missing something. Maybe I should consider A over here. That's going to be the first term, right? Is the first term. First term here is not 1 actually, because we start with n equals 1, but the first term is 1/2. Yeah, to have 1 over 2 here. Let me erase it. So 1 over 2, 1 minus 1 over 2, we are going to have 1 over 2 divided over 1 over 2 equals 1. So that top series is convergent to 1 because the bottom series, all partial sums are less than 1. And we know that partial sums are increasing. How do we know that they're increasing? Because every partial sum is going to add 1 over term. Because all terms are positive, it's going to be increasing. We're going to use the same theorem of monotonic bounded sequence. Our sequence is bounded, sequence of partial sums. This, if you build a sequence of partial sums, S1, S2, it's going to be bounded. All terms are going to be actually greater than each other. And it's going to be bounded by number 1, because we know that 1 is the limit of the top sequence and the bottom is going to be even smaller. And of course, it's going to be greater than 0. Why? Because all terms are positive. So we see that like terms are increasing greater than 0 less than 1. So basically this is monotonic bounded sequence is going to have a limit. So this one is going to have a limit or be convergent. So from this, we are going to probably make a conclusion that if something is less than convergent series, it's also going to be convergent. What is going to happen if something is less than divergent series? Let's consider example of something is less than divergent series. For example, I'm going to consider two series. Example number one. Let's consider a series 1 over n. We know that this series is divergent harmonic. And consider a series 1 over n plus 1. Well, this is not harmonic, but it's very close to harmonic. So we know that 1 over n plus 1 is going to be less than 1 over n. And we also know that this series, if we put like sigma here and sigma here, this one goes to infinity. If something is less than infinity, there is no actual conclusion about like what is it. Because something less than infinity can be another infinity or can be a number. So remember, if something is less than convergent series, convergent, then it's convergent. But if something is less than divergent series, we don't know. We do not know. Usually, we are going to know this, but kind of using a different test. Okay. Uh, maybe we should consider something which is divergent, like example of divergent series. Example number two. Example number two. Let's consider divergent series 1 over n and from 1 to infinity. And another divergent series, which is going to be 2 over n and from 1 to infinity. Well, I actually did a very, very kind of poor job of creating the second series, but we know that 1 over n is less than 2 over n, right? And we know that this series goes to infinity. So if something is greater than infinity, then this one must go to infinity because number cannot be greater than infinity. And we are going to say that divergent because this one is divergent. You see? So now I'm going to write down how the test works. The test works next way. Direct comparison test. Imagine that we have two series of an and series of, bn with positive terms. Number one, if series bn is convergent and the inequality between, sorry, I wanted to write down actually just inequality for terms, and an is less or equal than bn, then series an is convergent to. Number two, if series an is divergent and an is less or equal than bn. So the bottom, if this is divergent, then series bn is divergent too. Well, kind of our examples are working, right? Less than convergent is convergent, greater than divergent is divergent. So what are good series to do comparison? Useful series for comparison. When you do comparison, you will need to compare your unknown series with something known for which you do know for sure that it's convergent or not. So there are going to be two basic series. Number one is P series. We know that it's going to be convergent when p is greater than 1, convergent. When p is less or equal than 1, divergent. B, G series. I'm going to write down general formula for G series. A r to the power of n minus 1 and 1 to infinity. So the first term is A. For G series, the rule is r less than 1, convergent. I would say that I'm going to write down r greater or equal than 1. Well, generally speaking, it's not exactly divergent, but we're going to say that greater or equal than 1 divergent, okay? Good. Now, guys, sometimes it's going to be very easy to build inequality and kind of see whether the series is convergent or divergent, but sometimes it's going to be very easy to see from inequality. I'm going to consider example number 3. Remember, my first example was 1 over 2 to the power of n. It was a convergent geometric series with the sum equals to 1, right? Convergent G series. And I was comparing it to 1 over 2 to the power of n plus 1. And I see that because this one, the new one, unknown one, is less than my known one, that this one is convergent to. But what if my series, which I want to kind of investigate, is 1 over 2 to the power of n minus 1? We kind of understand that this minus 1 is not going to change the pattern because when everything goes to infinity, 2 to the power of n is going to be so huge that this minus 1 is not going to change anything actually. So we basically understand that this series is supposed to behave like this. But you cannot build a direct comparison. Actually, this series is going to be greater than 1 over 2 to the power of n. As you probably remember, it's not going to mean that it's divergent automatically. If this series, the bottom series, is convergent, then the one which is greater can be a different number, just like bigger number. Like, for example, this number is 1 and this number is equal to 2, just for example. It can be just a slightly bigger number. Or it can be infinity. So basically, when series is greater than some other series, you can, and that other series is convergent. You cannot tell whether it's like divergent or not, because it can be other number or can be infinity. Let me write it down in parentheses. It's 1. Actually, 2 can be greater than 1, and infinity can be greater than 1. So we don't know which one is this. Either it's a number or infinity, convergent or not. Well, what should we do? We understand that this second series is supposed to behave approximately like this 2 to the power of n, just because this one is very, very small. Well, when we are starting talking about something very, very small, we kind of recall the idea of a limit. Limit is going to deal with something which is becoming very, very small in comparison with something else. How about we just find the limit between terms of my known series and terms of my unknown series? Going to write down limit. Let's label this AN series and this one unknown series like BN series. I'm going to put BN term over term AN. So I'm not finding limit between series. I'm finding the limit between terms of series. So one element. Let's see what is the top one. 2, 1 over 2 to the power of n minus 1. And here 1 over 2 to the power of n. N goes to infinity. And let's simplify it a little bit. Flip over this fraction. 2 to the power of n, 2 to the power of n minus 1, n goes to infinity. And I'm going to divide by 2 to the power of n, numerator and denominator. So it's 1 over here minus 1 over 2 to the power of n. I'm trying to calculate this limit. Well, what I see, when n goes to infinity, this will go to infinity and the fraction will go to 0, and 1 over 1 is going to give me limit equals to 1. So I see that at infinity, these series are very close. That's actually limit of them is equal to 1. In case like this, and knowing that this one is convergent, we're going to say that this one is going to be convergent too. Well, just because we are adding basically at infinity very similar terms or like same terms. And we are coming after this example to another comparison test, which is called a limit comparison test. Limit comparison test is going to be very similar to comparison test. So, let's imagine that we have two series, AN and BN, with positive terms. And limit of AN over BN or BN over N equals to a constant number not equals to 0 and not equals to infinity. In our case, it was 1, but it can be 2. If all terms of the series is like proportional with coefficient 2, means that the sum is going to be twice bigger. You see? Then, what is conclusion? If series are kind of parallel, just proportional to each other, we're going to say that both AN and BN are either convergent or divergent. Means that, like, if one of them is divergent, another is going to be divergent, which one is parallel to that. Or if one is convergent, another one is going to be convergent. It's not important which put in numerator, which put in denominator, because if there is a number 2, for example, then if you switch them, you're going to get 1 over 2, which is still a number. So when do we use limit comparison test? We use limit comparison test when we cannot use direct comparison test just because inequality proof is going to be too complicated. I'm going to show you, let's say, a couple of examples of using a limit comparison test. And usually it's going to be comparison with P series, but let me kind of show you. So example number 4, I guess, right? I'm going to consider a series 3n squared plus 2n divided over n to the power of 7 plus 7. Yeah, guys, for this series, doing direct comparison is going to be too complicated because that's a rational expression, complicated one, right? So I see that I'm dealing here with kind of P series because if I deal with geometric series, it's supposed to be something like some number to the power of n. We don't have this. We have n to the power of like some number. What I'm going to do, I'm going to build comparison series. How I'm going to do it? Well, guys, like watch how I do this. I'm going to keep the highest power of numerator and the highest power of denominator. So I'm going to label it Bn. The highest power of numerator, let me get a different color, is going to be this term. So I'm going to write down 3n squared. The higher power of denominator, comparison 7 and n to the power of 7, of course, n to the power of 7. So it's a square root of n to the power of 7. And I'm going to simplify it a little bit. Simplifying is I'm going to calculate the total power of n, like in denominator. I'm going to write out 3. And in denominator, I'm going to put like n to the power of 7 over 2, right? This one is 7 over 2 minus 2. And I'm going to get 3 n to the power of 7 over 2, it's 3.5, right? So a net power here is 3 over 2 or 1.5. This is what? P series with P equals 1.5 greater than 1 convergent. Convergent. So I made my statement of conclusion. Now I'm going to find the limit. I'm not going to find the limit between my original series and this one, simplified version. I'm going to find the limit between my original series and non-simplified version. Again, because I want my life a little bit easier. Limit between AN and BN. Watch how I find the limit. I'm going to repeat it a second time with other series because sometimes people find it a little bit challenging to deal with all those limits. I'm copying my first series and then I'm copying my second. You are going to see why I did not simplify it. Guys, in this limit, I'm going to separate similar terms. For example, like fraction terms or like terms without square root are going to be separately, making a fraction 3n squared plus 2n. Sorry, my 2 doesn't look like 2 because of my pen. I'm going to read it. 2n 3n squared. I'm kind of combining similar terms together. And for the square root of n to the power of 7 over square root of n to the power of 7 plus 7. You are going to see why I'm doing this. Well, let's consider my first fraction. My first fraction, if I kind of deal with it, I see that I can divide here by n cubed, for example, or n squared. So I'm going to do it, or by 3n squared, actually. Well, I'm going to divide by n squared. If I divide by n squared, I'm going to put 2 over n here, and here is going to be just 3. This will go to 0 easily, right? So basically, my first fraction limit is equal to 1, 3 over 3. My second fraction, I can write down 1 square root n to the power of 7, n to the power of 7 plus 7. Well, here I'm going to divide by n to the power of 7, both numerators and denominator. So I have 3 as this limit, and this limit is going to be what? A square root of 1 plus 7 n to the power of 7, limit as n goes to infinity. And this will go to 0 again. So basically, sorry, 3 over 3, right? 3 over 3. I wrote 3 and forgot over 3. So I have the limit 3 over 3, that's square root of 1, which is going to give me 1. Usually, guys, if you pick up correct comparison series, your limit is going to be 1. So this is going to tell me that the limit is a number. This one is not equal to 0, not equal to infinity, means that it's a very nice number. And we know that one of this series, the bottom one, is convergent. We are going to say that by limit comparison test, my an series, which is like this complicated expression with square roots, is convergent to. Guys, when you say it's convergent to, it's supposed to relay actually to your statement that the other series is convergent. If you did not make this statement, you cannot make this statement too, because it's just like two what? You see? Okay. So limit comparison test. I think I'm going to consider one more example for a limit comparison test. And it's going to be, so normally, guys, that's a good way to pick up the comparison series. Just the greatest power of numerator, greatest power of denominator. Simplify it to make a conclusion about convergence, but use unsimplified version in the limit. It's going to be just making limit equals to 1, easy. Let me consider one more example. And that's going to be example number 5. Sometimes series are not going to be super simple. I'm going to consider series sine of 1 over n from 1 to infinity. Well, this is not actually like a rational fraction. It's a sine of a rational fraction. What actually we know, guys, from calculus? We know that sine of x is very close to x at small x. How do I know that x is going to be small? When n goes to infinity, we're going to have 1 over infinity, small numbers here. So I kind of assume that this one can be compared to the series 1 over n. What I know about this series, it's P series with P equals 1, also known as harmonic. And we remember that harmonic series is divergent. Oh, let's see how the limit is going to behave. Limit of sine of 1 over n over 1 over n goes to infinity. Here, guys, maybe we do substitution. Let's call x equals 1 over n. And we are going to have sine, sorry, then we are going to have a limit. When n goes to infinity, we're going to have 1 over infinity, so x will go to 0, right? we're going to have sine of x over x. Guys, here you can use L'Hopital's rule, or you can just know that this limit is equal to 1. We did cover it in calculus 5a. But again, if you feel comfortable to use L'Hopital's rule, use it. Normally, you expected to know that sine of x over x limit is equal to 1. Okay, we use this limit when we were proving derivative of sine. So the limit is not equal to 0, not equal to infinity, equals to 1 actually. So this series, the one of the series is divergent, so we are going to say by limit comparison test, the series AN is divergent to 3. So, well, guys, what you will need to learn well, how to pick up that comparison series. Usually we have two good comparison series, G series or P series. And for both, you will need to know how to pick them up like convenient, so your limit is not becoming like impossible to calculate. Okay? Well, I think that's all for comparison tests. Was kind of short chat section. My suggestion, do more problems on the homework, practice on those like kind of questions. And remember that terms of the series must be positive. And if the test is not working, for example, if you get a limit or for limit comparison, it's probably going to work all the time because the limit comparison test is just a limit, and if it equals to a number, it's going to work. If limit, for example, equals to 0 or to infinity, then the test is not working, then you will need different tests to check it. It does not mean that the series is divergent automatically if the test is not working. Test is not working means that, well, you'll need a different test. This is just a bad tool to investigate the series. Okay, I think that's all for today and kind of practice with homework and my practice problems. Okay, thank you.